Good morning. Today is Chapter 5. We're going to begin Chapter 5 beyond our description in the face-to-face class. In Chapter 5, the first section is 5.2 entitled Random Variables. Alright, we all know what random variables are. From our face-to-face class, we know it's a variable whose values are randomly determined by experiment. Recall Chapter 5 is entitled Probability Distributions. And we know from class also that a probability distribution distributes one unit of available probability in any experiment amongst all possible values of a random variable. Alright. Chapter 5, the author has a descriptor in that title. It's entitled Discrete Probability Distributions. Well, I would probably just call it Probability Distributions. We'll talk about the discrete part a little bit later in the class. Alright, let's brief refresher on what we did in face-to-face class. Let's perform an experiment. Statistical experiment. I'm going to have 4 children. Alright, and record the gender of each child. Familiar scenario. And within that experiment, I'm going to define a random variable. I'm going to let x equal the number of boys in 4 births. Okay, in those 4 children. Alright, well, you may ask yourself, how many possible values of x are there? Well, let's make a list. I suppose the minimum number of boys in 4 births that you could have is 0. You could have 1 boy, you could have 2 boys, you could have 3 boys, or you could have 4 boys. So there's 5 possible values for x in this experiment, 0 through 4, the integers 0 through 4. Now I'm going to want to distribute the probability amongst all possible values of x. In other words, create a probability distribution. Well, what's the probability that x is 0, that you've got 0 boys in 4 births? Now again, we're assuming boys and girls are equally likely, the familiar scenario, in any birth, and that the gender of any one birth is independent of the gender of any other birth. Well, in 4 births, we've got 16 outcomes, right? And out of those 16 outcomes, only one has 0 boys. That means all girls, right? Girl, 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 right? Alright, similarly, let me go down to the list here and find the probability of 4 boys in 4 births. Well, again, you've got 16 outcomes in 4 births, allowing any child to be of any gender in any order, and only one of those outcomes has 4 boys, right? Alright, let's see if we can use a little detective work to fill out the rest of this table. Let's look at the probability of 1 boy in 4 births. Well, you've got 16 outcomes total. And let's ask ourselves, how many of those outcomes have 1 boy? Well, if you've got 4 births, you've got 4 different slots available for that 1 boy. So I've got 4 outcomes that have 1 boy. Right? Boy, girl, 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 boy, girl, 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 boy, girl, and girl, 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 boy. Alright, similarly, what's the probability that x is 3, that you've got 3 boys in 4 births? Again, there's 16 outcomes. And how many of those outcomes have 3 boys? Well, of course, 3 boys means 1 girl. And it's somewhat similar to the 1 case. If you've got 1 girl, you've got 4 different slots available for that 1 girl. Alright, so 4 outcomes out of 16 involve 1 girl or 3 boys. Alright, now I'm going to use a little detective work to figure out the probability that X is 2. There's a lot of ways to arrange 2 boys and 2 girls. I won't try to list them all here. I'll just use my finesse and say that I know in any probability distribution the sum of all the probabilities have to equal 1, and each probability, of course, by definition, has to be between 0 and 1. Alright, so what I can do is add up these fractions and subtract from 1 because I know this column has to add up to positive 1. So I can then claim the probability that X is 2 is going to be 6/16 to meet this requirement that all the probabilities have to equal 1. Alright, so there's another probability distribution. In class we did the X equals number of girls in 3 births, I believe it was. So here's the 4 case, constructing the probability distribution for number of boys in 4 births. Alright, this is what we call a discrete probability distribution. And by discrete, we mean not continuous. Let me put it this way: the random variable X is not on a continuous scale. If you look at these range of X values, X can be 0, X can be 1, but X of course can't be anything in between 0 and 1. So if your values of your random variable are separated by disallowed values, we call that a discrete random variable, and hence we call this probability distribution a discrete probability distribution. In math, discrete very simply means separate or disconnected. Okay? Alright, when we're given a probability distribution, much like when we're given raw data, we're going to ask 2 things. What's the center, and what's the spread of all these possible X values? Now notice we're given the probability of X, certain cases of X in this table, and what I can do is use these table values and a couple different formulas to compute the mean and standard deviation for X. So that's coming up next. We want to compute the mean and standard deviation, and also the variance for any given probability distribution and random variable within that probability distribution. Alright, so this is our next goal, and I'll get a fresh screen. Alright, if I'm given a discrete probability distribution in table form, as we did just above, I'm going to give you a couple formulas first to compute the mean and the standard deviation for a probability distribution. The mean of a probability distribution we will symbolize with the Greek letter mu, the lowercase Greek letter mu. And it's a simple formula to compute the mean. You take each possible X value and weight it or multiply it by its associated probability. That's all there is to it. Now the standard deviation for a probability distribution, much like standard deviation for data, it's a little bit more involved. This involves what the book calls a shortcut formula. There is a longer way to do it. I'm going to take the shortcut formula the book uses. Alright. So basically I take each X value, first square it, then multiply by the associated probability, then add up all these products. Once I've got that value, I subtract the previously computed mean squared. So much like in computing SD from raw data, when you compute the SD from a probability distribution, you have to know the mean to do it. Unfortunately, our calculators are not pre-programmed to handle these two formulas, so these you're going to have to grind out by hand, and I'll show you how in a column fashion here right now. Oh, by the way, the variance of a probability distribution, as you might expect, it's going to be sigma squared, simply the square of the standard deviation. Well, it's the above formula without a square root symbol. Okay? So this is U is the mean of a probability distribution. Sigma is our SD of a probability distribution. And sigma squared, of course, the square of the standard deviation is the variance of a probability distribution. Okay? Alright, let me give you an example of how to compute this, and it's a little tedious, but with a practice session or two, you should be just fine. The book cites a table in page 205. See table 5-1 on page 205. What they're doing is performing a scientific experiment. They're printing the results of this study where 5 pea pods were grown and the number of green pea pods were recorded and probabilities assigned. And I'm going to let X equal the number of green pea pods in 5 grown pea pods. All right, well, if you're talking about number of green pea pods in 5, the first thing you want to ask yourself is how many values can X attain? Well, the minimum number of green pea pods you could have is 0. You could have 1. You could have 2. You could have 3. You could have 4. And you could have 5. Okay? Alright. Our experimental data is recorded, and based on the study, all these possible values for the probabilities of green pea pods are as noted here. Let me take a minute to copy them all down. 7. Alright. Alright, I'm going to ask us now to compute, using the above two formulas, compute the mean and the standard deviation for this probability distribution. Now, the first thing I'm going to do is guess. The mean for the probability distribution is, let's say, I'm going to guess it's somewhere in this range. Somewhere between 3, 4, and 5, because if I see these values, these X values of 3, 4, and 5 seem to be more likely than the values 0, 1, 2. They're higher probability values. So I'm going to guess if I perform this experiment a large number of times, I'm going to guess that the mean number of green pea pods is going to be somewhere in the range of 3 or 4 or 5. Let's see if we can confirm that with the calculations. The mean equals mu equals summation x times p of x. So all we'll do is take each x value and weight it or multiply it by its associated probability and add up all those products. This is a little tedious. Let me write it all out here nice and clear. Of course, you'll probably want to use your calculator to maximum advantage here and let the calculator do most of the work. Alright. So after I perform all these multiplications and add up these products, I will end up with a mu value of 3.752. That is the mean of my probability distribution. And remember, that kind of jives with what I was guessing at. If you were to perform this experiment many times, you would expect the most likely value of x to be somewhere in the 3 or 4 or 5 range, right? Just short of 4 as the calculator shows us. Okay? Alright, so that's how you compute the mean, and that's not such a bad calculation. Let me put this value aside because we're going to need this to compute the standard deviation next. Okay? Alright, let me erase. I'm going to leave that table there. So let me erase the mean calculation because now I want to compute the standard deviation. Alright. So I think we'll have enough room. Alright. Recall the standard deviation of a probability distribution. We call it sigma. It's like a population SD from raw data, same notation, and it's going to be the square root of the sum of the square of each x value multiplied by its associated probability minus the square of the previously computed mean. Alright, don't panic. I'm going to make a third column here. And as you might expect, I'm going to call it the x squared times p of x column. So basically I'll take each x value, square it first, then multiply it by its associated probability as noted in this table, and then the sum of this column will be this term under the root sign. And the worst will be over once I get that sum of that third column. So let me go ahead and square. Well, let's see. 0 squared is 0, and 0 times anything is 0. Well, that was easy enough. How about 1? 1 squared is 1, and 1 times 0.015 is 0.015. That wasn't too bad either. I've worked these out already. 2 squared is 4, and 4 times 0.088 is 0.352. 3 squared is 9, and 9 times 0.264 is 2.376. 4 squared is 16, and 16 times 0.396 is 6.336. And last one, 5 squared is 25, and 25 times 0.237 is 5.925. Alright, so I now need the sum of all these products, and that's merely the sum of this third column. And if you take the time to add them up, I already did it ahead of time, it's 15.004. Now I'm going to keep as much decimal accuracy as I can stand here. Let's see, again, how far you want to round off is essentially your choice. I'm not going to insist on 10-digit accuracy on each and every calculation, of course. Alright, so this 15.004 goes here under that root sign in our sigma calculations. So sigma is 15.004, or the square root of 15.004, minus the previously computed mean. Now remember, that was 3.752 squared. And if I punch this out in my calculator, according to my order of operations, I get 0.962. Voila. That is your standard deviation calculation from a probability distribution. Okay? Alright, we're ready now to compute the variance. Well, of course, the variance, by definition, is the square of the standard deviation. So if I take that value, 0.962 squared, I end up with 0.926. Alright, so there's an example of how to compute the mean, standard deviation, and variance from a discrete probability distribution given in table form. All right. The book talks about unusual values again, but now in the context of a random variable. So let me write unusual values. Let me put that in quotes. Unusual values for a random variable x. And this is going to look very familiar. Basically, and somewhat arbitrarily, we're going to define usual values of a random variable as being within 2 standard deviations of the mean. Alright, so if we can compute a mean from a probability distribution, we can compute a standard deviation from a probability distribution. We can also compute these boundaries for unusual values, and you'll see this come into the homework problems. Anything beyond these limits, of course, we are going to claim are unusual. Okay? I want to talk now about expected value of a random variable. Let me write that down. Expected value of a probability distribution / random variable. Expected value, I'm going to symbolize it with a capital E. And all it is the same formula for the mean of a probability distribution. That's all it is. Okay? So what happens is the author has introduced this formula, right, and uses the phrase expected value in using game of chance type calculations or in insurance company type problems stated in the text. So let me write that down. Use in game of chance type problems or insurance applications, as we'll see in the homework list. Okay, so anytime you see expected value, in our author is just taking this convention, typically means a game of chance type application. Alright, let me give you an example of how the author might play this out. And this is a pretty interesting example. Let me get a fresh screen. Example. Let's play a game of the New York State daily number. And how we do that is we pay $1 and then pick a 3-digit number. Now I may be simplifying the rules of the game a little bit for the purposes of clarity. Alright, so we'll pay $1 and pick a 3-digit number. Alright, if the number hits, in other words, the 3-digit number that you picked comes up, you win $500. Okay? What I'm going to do is construct a probability distribution and then compute the expected value for this probability distribution. I'm going to say let x equal the net winnings in dollars for one play of this game. Okay? Alright, I can, let's see, let me write this down. I'll say construct the probability distribution for x and compute the expected value for x. In other words, how much can I expect to win in any one play of this game if I play this game for a large number of times? Alright, let's do the probability distribution first. How many possible values of x are there? Well, you either win this game or you lose this game. All right, there's only two outcomes, and money-wise, if I lose the game, in other words, my number does not hit, I lose $1. So my net winnings in that case are going to be negative $1, right? Let's say I win this game. Now remember, x is your net winnings in dollars. If you win the game, you win $500, but you've got to subtract off the dollar that you invested. So my net winnings in that case would be $499, right? Now both of these outcomes for x occur with different probabilities. Now, if you're picking 3-digit numbers, you have to ask yourself how many different outcomes are there. Well, of course, there's 1,000 3-digit numbers from 000 to 999. And only one of them is a winner. So if you win, that happens with probability 1 out of 1,000, right? If you lose, which happens almost all the time, that happens with probability 999 over 1,000. Okay, so there is my constructed probability distribution for x. Now I want to compute the expected value. Expected value is nothing more than the mean of the probability distribution. And let me write it out here. I take each x value, weight it or multiply it by its associated probability. Hang on a minute. $499 times 1 over 1,000. Alright, so if I multiply those fractions and add or subtract as indicated, I'm going to get, let's see, an expected value of minus 500 over 1,000, and that's minus 0.5. Minus 0.5. Well, minus 0.5 what? Well, your expected value is in dollars. If your random variable is in dollars, that means your expected value is in dollars. And I think you know where we're headed here. It is certainly no accident that this is a negative expectation. And typically all games of chance, all casino or lotto or lottery type games of chance have a negative expectation, are designed to have a negative expectation for the player. All right, this expectation tells me you're going to lose 50 cents on average every time you play this game. Again, on average, in the large scheme of things, we will lose 50 cents every time we play this game. And that's how the state makes money on these games. Once in a while you win, almost every other time you lose, and the state can expect to make a profit of 50 cents for each lottery ticket they sell, again in the large scheme of things. Okay? Alright, I want to talk about one more problem before we call it a day, and that's an insurance type application. And this is number 29 on page 217 in our text. Alright, I'm reading from the text, number 29, expected value for life insurance. There is a 0.9986 probability that a randomly selected 30-year-old male lives through the year. A Fidelity life insurance company charges $161 for ensuring that the male will live through the year. If the male does not survive the year, the policy pays out $100,000 as a death benefit. I'm going to focus on part B. If a 30-year-old male purchases the policy, what is his expected value? Alright, so let's see. I'm going to construct a probability distribution for the net gain this man would have from the insurance policy. So let me assign the random variable. I'm going to say let x equal the man's net gain in dollars from this policy. Alright, well, there's two values of x based on whether this man lives or dies in the year of the policy. Well, if the man lives, there is no payout from the insurance company, and essentially the man loses the $161 he paid for the insurance policy, right? But if he dies, the insurance company pays out $100,000. Now, I'm assigning x as a net gain, so I have to take $100,000 and subtract the $161 that he paid for the policy, and that leaves me a value of $99,839 that the insurance company would pay out in the case of the man's death. Okay? So two values of x, negative 161 and positive 99839. Be careful of those signs. Both of these outcomes occur with different probabilities. Now we are told explicitly in the problem that the probability that a man will live through the year without calamity is 0.9986. 0.9986. Let me erase that. 0.9986. Okay? Well, what then is the probability that the man will die? Well, of course, it's going to be the complement of 0.9986. I just subtract that value from 1, and I get 0.0014. Alright, so now that I've constructed the probability distribution for the net gain in dollars from this policy, I can now compute the expected value. Expected value is nothing more than the sum of each x value weighted or multiplied by its associated probability. So minus 161 times 0.9986 plus 99839 times 0.0014. And if I multiply correctly and add this up, I get an expectation of negative $21. And much like the lottery exercise we just did, this negative sign is not there by accident. This represents the insurance companies, this negative 21, represents the insurance company's profit on that one individual policy for the year. So, and again, in the wide strokes, in the wide scheme of things, the insurance companies are out to make money, and this is how they do it. And most people will live through the year without any calamity, and each person that lives ends up paying out $21 to the insurance company for the privilege of the security. Okay, so let me write that down. This represents the profit of the insurance company from any given policy, from this policy and really all policies like it. Okay. Alright, I think we're ready to call it a day. We're reaching the 37-minute point, and please be sure to review all materials before you complete the online exam. Random variables, probability distributions, and expected values type problems in games of chance, and insurance type applications. That's all.